Welcome everybody. We're going to do a lesson about function transformations. So this is our fourth lesson in the functions unit. We started off with definition, and then we took a look at the graphs of functions and domain and range. And then we also talked about piecewise functions, which is kind of like a funky way to define functions in parts. And now we're going to talk about how you can transform functions by moving them around, up and down, and stretching them, and flipping them, and so forth. So this is all a very visual kind of task that we're going to do with functions. And we'll look at it algebraically, and we're going to look at it graphically. So, all right, let's dive into transformations. So there's three kinds of function transformations that you can do. One of them is a translation, and that is where you're taking your function and you are moving it horizontally or vertically, and so you're keeping everything the same. The shape of the graph doesn't change. It's just getting shifted around the axes, okay? So a translation is one thing you can do. You can also do a dilation, and the dilation just stretches the graph or squeezes it together. And you can stretch it horizontally, or you can stretch it vertically, or you can compress it vertically, or you can compress it horizontally. So those are different kinds of dilations you can do. And then the last one is a reflection. That's where you take your graph and you kind of spin it, or think of it as like looking at it in a mirror. What would it look like if you were to reflect it across a vertical line? So that's like doing this kind of reflection. Or what we had to do if you were to reflect it across a horizontal line, that would be like doing this reflection. Kind of like spinning this way or spinning that way with your graph. Okay, so let's dive into translations. Okay, for all of these examples, everything holds no matter what the function is. Okay, so f is going to just stand for any function. You know, it could be x squared, it could be a linear function, it could be a cubic, it could be a square root, it could be an exponential. It doesn't matter what the function is. These translation rules always apply to those functions. Okay, so doesn't matter what f is. So that's why we're going to write our rules in terms of a general function f. All right, so we'll first look at a vertical translation. We're going to make a new function, and it's going to be based off of our general function f. So we're going to call this one g. So let g be the function that is whatever f is, f of x plus a. So you're going to add a after you apply the function f to your input. What does that do? Well, you get the graph of g by shifting the graph of f vertically by a units. So if a is a positive number, you're going to shift your graph up by a, and if a is a negative number, you're going to shift it down by a. Okay? So it's just moving your graph, all the points on your graph, up or down. Okay? So what this means is every point on f's graph gets a added to its y coordinate. And let's look at an example. Okay, so here's a function f of x equals 2x plus 1. That's a linear function, right? It's a line with slope 2 and y-intercept 1. And then we're going to base g off of f. We're going to say g of x is f of x plus 3. So we're going to take the function f, whatever we get as the answer, we're going to add 3 to it. Okay? So we're going to get g's graph just by shifting all of f's points up 3 units. So this is what it will look like. So the red graph over here is our f of x. So this is f of x. And that's given the rule 2x plus 1, linear function, right? We can see that point 0, 1 is on the line, 2x plus 1. We also know this point 1, and that's 3, is also on the line, 2x plus 1. And what happens when we want to graph g of x? So g of x is our blue graph. And when we want to graph that, we're going to just take all these points and shift them up 3. So everything goes up 3. Everything goes up 3. So we're moving the whole line up 3 units. So this is plus 3 units. And so where do these points go? Well, we can take a look and say 0, 1. We're adding 3 to its y value. So this is 0, 1 plus 3. That's what we're going to get, because we're adding 3 to the answer. And what's that? Well, that's 0, 4. So that's that's equal to 0, 4. And that's right there, this point up here, 0, 4. And similarly, if we took the point 1, 3, which was on our red graph, and added 3 to its y value, you're going to get 1, 6. This is 1, 6 right there. Okay? So all those points, every single one of them gets moved up 3 units by g in this case. Okay? And that would work no matter what f is. This is just a particular example for f. If f was a square root function, this g function would still take all its values and shift it up 3. If f was a quadratic, it would still take its y values and move them up by 3. Okay? All right, so got another example. Or rather than another example, let's move on to horizontal translations. Okay, so horizontal translation is going to be defined as the function f of x minus b. So what that says is that we're going to move our graph b units horizontally. So we're going to get g by taking whatever f is and shift it horizontally by b units. So b units to the right if b is positive, and b units to the left if b is negative. Okay, so that's how it moves around. So what this means is that every point on f's graph is going to have b added to its x coordinate. Okay, one thing that's tricky for students with these is that on the inside, so this is inside with x, it's always doing the opposite of what it looks like it's doing, in the sense of it looks like I'm taking away b from our x coordinates, but we actually end up having to add b to get the right values. So what it does is it's going to move everything to the right by b, even though it's got a minus sign, which makes you think it should move it left. Okay? All right. We'll kind of dive more into detail about that, but it's confusing, and it's a rule that you can just memorize for now. But if you're really curious, like, why is it minus? Why is it minus? I'd love to have that conversation with you, because it is there's a lot. There's not a lot, but there's some stuff there to talk about. Okay. So let f of x be the function x squared. And we'll have the graph we're going to call g f of x plus 1. So rather than f of x plus 1, we're going to add 1 to our inputs and then apply f. So it's a little bit of an ordering thing here. We take our inputs, add 1 to them, and then apply the function f. That's how g is defined. So how do you get g's graph? Well, you're going to take the graph of f of x, which is x squared, and move everything left 1 unit. All right, so here's our function x squared, f of x equals x squared, and it's got those key points we know about, 0, 0 in this case, and 1, 1, and even the point up here we could say is there's 2, 4. I didn't plot it, but it's right there. And so we take all those points and we take away 1 from their x values. So we're subtracting 1 from all of their x values in this case. And because this is, our function was f of x minus b, means add b to everything. And in this case, this is f of x minus negative 1. And so we're adding negative 1 to everything. Okay, so everything gets moved left by 1. All right, so where did those points go? Well, 0, 0 is now here at -1, 0. And 1, 1 is now here at 0, 1. And 2, 4 is now here at 1, 4. Okay, so everything got moved left 1 unit. Okay, so we took the whole thing and we went left by 1 unit. Okay, so that's how we got the graph of G from the graph of F. So again, 0, 0 went to -1, 0. 1, 1 went to 0, 1. We're taking 1 away from each of their x coordinates. All right. So you can have a general translation function, one that's not just up, down on its own, left, right on its own. You can combine these two into one function. F of x minus b plus a is going to shift the graph horizontally by b and vertically by a. So it's kind of combining those two into one function. And so what that means for all the points is that every point on F is going to get a added to the y value and b added to the x value. So you're just moving all those points, all the y coordinates up or down by a, and all of its x coordinates left or right by b. So let's look at an example where we do both of these shifts. So we're going to have a function, square root function in this case. Again, remember, this doesn't matter what f is. G is still going to shift that function no matter what f is in this manner, okay? So we're going to say g of x is f of x minus 2 minus 3. So take a minute to think about how you could describe that translation. You know, what would you say to someone to tell them how would they move it? So if you want to take a second to think about it, I'll tell you what the how you would do that. Okay, so in this case, f of x minus 2 minus 3 is going to move the graph right by 2 and down by 3. So we're shifting every point of f right 2 and down 3, which means we're adding 2 to all the x values and subtracting 3 from all the y values. So let's see how that works. Here's the square root of x. So this is f of x, again in red. That's root x. And it's got some key points here graphed, 0, 0 and 1, 1. And there's also this point over here, 4, 2, which we could label as well. I did not. And so we've got those 3 key points. And where do they go after this transformation? Where will they show up on G's graph? Well, you're going to move all of them right 2 and down 3. So let's go ahead and do that. So 0, 0, if I move you right 2 and down 3, you end up right there. So you're going to be at 2, negative 3. 1, 1, if I move you right 2 and down 3, you're going to end up right here at 3 and negative 2. And then 4, 2, if I move you right 2 and down 3, you're going to end up here at 6, negative 1. Okay? So each of those points gets moved to that new place on the graph of G. Okay? So what we're doing, again, we're adding 2 to the x coordinates. So 0 plus 2. And then we're taking away 3 from the y coordinates, 0 minus 3, and that's how you get 2, negative 3. 1 plus 2, that's a plus 2, and 1 minus 3. That's how you get the new location for that point. All right? Okay, so that's a translation. All right, now let's take a look at dilations, which are just like similar to translations. Instead of moving the thing left and right, up and down, now we're stretching it vertically or horizontally. We're going to break it apart into its 2 chunks, the vertical dilation and the horizontal dilation, and then combine those 2 together. So if you take a function f and then you multiply it by some constant, you end up stretching the graph vertically by that amount. So c times f of x is a vertical dilation on the graph of f by c. So by some factor, you know. So if C is more than 1, you end up making it taller, you stretch it out. If C is less than 1, you end up compressing it. Let's go ahead and just write that down as a note so that we can keep that in mind. C being more than 1 makes it taller, and C less than 1 shrinks it, makes it shorter. That's going to compress it. Okay, so that's kind of the key value for this for what happens to the graph is 1. If it's more than 1, you stretch it out. If it's less than 1, you squish it down. Okay, so this what it means again for the points is that you're multiplying all of their y coordinates by c. So you look at your points on F, you take their y values, multiply it by c, and that gets you the where it should be on the graph of G. Okay, so let's look at an example. So here we go with the linear equation, 2x plus 1. The graph g of x equals 3, f of x is going to be a vertical stretch by a factor of 3. So we're going to take all the points on 2x plus 1, and we're going to multiply their y values by 3. So it's going to get steeper. It's going to have a larger slope. We're going to take all their y values, multiply them by 3, and this is the graph that you'll get for G. So I'm going to just mark out some points on the graph of x. So here's 2x plus 1, our line with slope 2 and y-intercept 1. And so we've got these points like 0, 1, and 1, 3. And where do they end up? Well, we're taking their y values and multiplying them by 3. So let's take the y value of the first point, which is 1, multiply it by 3, and you end up getting 0, 3. So it's up there now. And then let's take the y value for 3, multiply that by 3, and you end up getting 1, 9. So it's been stretched vertically. We end up having a steeper graph as a result of it. Okay, so those points went to those locations, 0, 1 went to 0, 3, 1, 3 went to 1, 9. One thing to note, this point that's on the x-axis, I'm going to graph it kind of in green right here, this point right there, whose y-coordinate is 0, didn't get moved by the dilation. And I'll have you try to think about why that point didn't go anywhere when we stretched it by 3. Its y-coordinate is 0. So what do you think happens when you multiply that y-coordinate by 3? All right. So let's look at horizontal dilations. So horizontal dilations behave similarly to horizontal translations, and that the way it looks is the opposite of what you think it would be. So rather than multiplying by d on the inside, we actually divide by d, aka multiply by 1 over d. And what this will do is we'll stretch the graph of f, horizontally by a factor of d. So we're going to stretch it horizontally by whatever d is in this case. And the same reasoning applies. That means we're going to multiply every point on f's graph, multiply its x coordinate by d. So whatever d is. Okay. Let's look at an example. Here's a function x squared, and we're going to graph f of 2x. Okay. So let's see what that will do. Well, it's not completely obvious because it doesn't look like f. It doesn't look like f of 1 over d x yet. But let's go ahead and turn it into that. So this is f of 1 over 2. x. Okay, so f of 2x, let me actually write this over here. I'll erase this. So f of 2x is actually f of 1 over 1/2 x. All right, and so that's our d. That's the value of d right here. We are going to multiply every x coordinate of f's graph by 1/2. Okay, so it's the opposite of what you thought it would be. You thought, oh, f of 2x, I know what that's going to do. It's going to double everything. It's going to make it wider, but not so. It actually compresses it. It multiplies everything by 1/2. So the graph becomes tighter together. It's going to squish in. Okay? So that's what f of 2x looks like, the blue graph. Let's just look at these points, see how they move. So here's f of x is x squared in this case. So we've got some key points to look at. 1, 1, that's one key point. 2, 4, that's another key point to look at. 0, 0, where did that guy go? 0, 0 didn't go anywhere. But let's look at 1, 1. So we take its x coordinate and we multiply it by 1/2. So now it's 1/2, 1. 2, 4, where'd that go? We take its x coordinate, multiply it by 1/2, and so it's now 1, 1, 4, just like that. Okay, so it got tighter together, everything kind of compressed by a factor of 1/2. So we went in, and the farther out we were, the bigger that step is because we cut it in half, okay? So this is times 1/2. That's how we did that, 1/2. That doesn't look like a half. Let's turn that into a half. Times by 1/2 on all the x values. So you can see how that works with these points, with these numbers. 1, 1, multiply its x by 1/2, you get 1/2, 1. And 2, 4, multiply its x by 1/2, and you get 1, 4. And you can do that for any of the other points on our graph, and you'll get g from that. Okay, all right. Last one, or no, last dilation, is that you can combine them. Again, you can do both a vertical dilation and a horizontal dilation. And so what that's going to look like is something multiplying on the outside and something multiplying on the inside. So the thing on the outside is direct multiplication of the y coordinate. The thing on the inside is the opposite. You do 1 over that to figure out what to multiply by for those points. Okay, so we stretch it vertically and stretch it horizontally. So it's getting stretched in 2 ways for this kind of function. All the y coordinates will get multiplied by c in this case, and all the x coordinates are going to get multiplied by d in this case. All right. So here's an example where we've got both of them going at once. G of x is 3f of 1/2 x, and our example function is root x. So what is that going to do to our function? 3 times 1/2 x, or 3 times f of 1/2 x. So in this case, we can read off the c value is 3, so it's going to stretch it vertically by a factor of 3. So it's going to make it taller. The d value is right here, that's 2. So d value is 2, and c value is 3. So it's going to stretch it wider by a factor of 2. So we get a taller, wider square root function. Okay? So we stretch it vertically by 3 and horizontally by 2. So let's look at some points. How did they get moved? So let's look at, so 0, 0 didn't go anywhere. We knew that wasn't going to go anywhere because when you multiply 0 by 3, or excuse me, multiply the x by 2, you get 0 still. You multiply the y by 3, you get 0 still, so it doesn't go anywhere. So we got 1, 1, that's on our graph. And we'll also look at 4, 2. That's also on our square root graph. So where do those guys go? Well, we take the 0.11, we're going to multiply it by 3, and that's going, multiply. You can do this in any order. You can either do the horizontal or the vertical first. It doesn't really matter which way you do it. But let's do the, let's do the horizontal first, for example. We multiply the x by 2, so that's going to move it here. It's kind of an interim point. Then we multiply the y by 3, that's going to move it up here, which is the point 2, 3. So we multiply the x by 2 and the y by 3. And then let's look at 4, 2. We multiply the x by 2, that takes it out to 8. And we multiply the y by 3, that takes it up to 6. So here we go, 8, 6. That's where we land after doing that. So we stretched it horizontally by 2, vertically by 3. Again, what that looks like is we're doing 2 times 1 and 3 times 1, and that gets you 2, 3. And this point over here, we're doing 2 times 4 and 3 times 2, and that gets you 8, 6. That's where we end up. Alrighty. Last but not least, before we call it, you can do reflections as well. A reflection across the x-axis means you're changing the y values. When you're moving it across the x-axis, if it was a positive y, it's now a negative y. If it was a negative y, it's a positive y. That's multiplying the y values or the outputs by -1. So that's a reflection across the x-axis. Excuse me. Something caught in my throat. So you graph G by reflecting, taking all the y values and flip-flopping their sign. Okay, multiply them y values by -1. To reflect across the y-axis, then you take all of the x values and flop those. Okay, so all the x values, if it was a positive x, it becomes a negative x. If it was a negative x, it becomes a positive x. So that's how you do that reflection across the y-axis. And so the negative shows up on the inside instead of on the outside because it's affecting the x values to do it that way. So you multiply all the points x values by -1 in this case. Let's just do one small example of one reflection. You can combine the two reflections with just two negative signs, one on the outside and one on the inside. So we are going to start with the absolute value of x graph, and then we're going to reflect it across the x-axis by multiplying the y's by -1. So reflecting across the x-axis, you just get this picture. The starting graph is red, that's absolute value of x. You reflect it across the x-axis, means take all of those points. They were positive y values, now they become negative y values, and so they all show up down below the x-axis. Okay, so that's our video about, all right, right in the middle. That was our video about transformations. That's kind of the first step, is we built out all those blocks. What's a translation? What's a dilation? What's a reflection? Can you combine these translations? Can you combine these dilations? Yes, you can. So the last step is to actually put it all together. So come up with one general transformation function that has translations, dilations, and reflections all together in one, and kind of make a rule for it, and then we can apply that general transformation, and I'll show you rules on how you would want to apply that general transformation function. But that's it for this lesson. Hopefully you guys have a good weekend, and I'll see you all on Monday.